Okay. Okay. Yeah. So we're recording for later. So the first problem was the one from the homework, and this one had a system where we had these three lines that were essentially in parallel with each other, and this had some battery that had some potential difference across it, V2. And then this was a resistor R3, this was a resistor R2, and then this was a resistor R1. And then this was a battery. With this is some V1, this is a minus plus, plus minus. Okay, so as I'm going through these, if you have any particular favorites that you'd like me to go through, if you've been looking at some old exams, let me know. One thing I was talking to Laura about this because several students had questions at the beginning of class that she was gracious enough to answer before I got there. And part of the crux of some of those questions was, how do you define the current? We know that there should be some preferred direction that the current is going to flow in. And what I've done to this point is I said, well, it doesn't really matter what the preferred direction is. You can always just define it whatever direction you want. And then when you do your loops, it'll come out in the end that if the direction that it actually goes is the direction that the current does actually go in, that'll have some positive sign for the current when you do the algebra at the end. Or if it's opposite the direction, it's going to have a negative sign. But to a lot of you guys, and actually to me when I think about it as well, that's a little bit unsatisfying because you know the current should go in some direction. So wouldn't it be nice if we just labeled what the direction the currents went in the actual direction they went at the onset of the problem, rather than saying, well, I'll choose one, it goes this way or that way. And the real answer to that is that the current, and I've actually implicitly been doing this as I've been defining these without telling you that that's why I chose them. The current is going to flow from positive to negative. So when I define these currents, a way to do this to make it so that you minimize the number of negative signs that you have is to define the current so that it goes from the negative terminal to the positive terminal. So if I was going to define the current for this situation, the way that I would do this is I would say that this would be the current I1. I was already getting ahead of myself. We'll get to I2. This is the current I1 because it's flowing away from the positive, and when it comes over here, it's going to be flowing towards the negative. For this current that I have down here, I would say that this is going to be some I3. And the reason why I'm calling it I3 is because it's going to go through the resistor R3. Now, this one right here, this is where we get into the place where we could have some arbitrary things going on. Because we really don't know what the direction the current should flow in this one, because it depends on what the relative magnitude of V1 and V2 are. If V1 is larger or V2 is larger, will tell us what the direction this one goes. So for this one, you really do have to pick a direction. And so I'm just going to pick this going to the right. Okay. So when we look at this circuit, we have everything labeled that we need. So we don't have any capacitors. There's no charges to label. We've labeled all the currents. And so the first thing that I'm going to do is to draw some junction here. All right. So this is the box that I use for the integral of J dot ds is equal to minus dq dt, which is equal to 0. Okay. So for this box, what I end up seeing is when I evaluate the integral of J dot ds, this is going to give me some minus I1 minus I2 plus some I3. And so the way that you can see this is anything that goes into this is going to be negative because the current density is going to be opposite direction of the ds vector. And anything that goes out of it is going to be positive. Now, I like to write these things in the most general way possible, but if you're not satisfied with that, you can write this in an alternative fashion to say that the sum of the current into the junction is going to be equal to the sum of the current that goes out of the junction. And that's not equal to 0. They're just equal to each other. Okay? And ultimately, they give the same thing. So what this says when I rearrange this is that I3 is going to be equal to I1 plus I2. Okay? So now the next thing that we can do is we can draw some loops to evaluate here. And the loops that I'm going to draw, again, you can draw them clockwise or counterclockwise. If you want to do this again in a way that minimizes the number of negative signs, I would draw this one going this way. That one actually doesn't minimize the number of negative signs. But if I do this one this way, it does. So call this loop 1 and call this loop 2. Okay? So the integral around the closed loop of E dot dl is going to be equal to 0. And this is true both for loop 1 and loop 2, but we'll look at loop 1 first. And so what this says is, going around, if I start over here, this is going to go across the resistor in the same direction as the current. So this is going to say that this is going to be I1 times R1. Now, when I get to the battery, I see a negative sign here, and so this is going to be minus V1. Coming around down through R2, the current is going to the left, the loop is going to the right, and so this gives me a minus I2 times R2 is equal to 0. Okay? So now let's look at loop 2. Integral around the closed loop for loop 2 of E dot dl is going to be equal to 0. And so again, we can start over on this side. When I go across R2, this is going to give me a plus I2 R2. And then coming around this way, I'm going to see a negative sign when I get to the second battery. So this is going to be minus V2. And then this is in the same direction as I3. And so this is going to be plus I3 R3 is equal to 0. Okay? So then let me see if there was any simplification made here. So for this problem, what they say is if V1, so if we say that V1 is equal to 2V2, how must R1 and R3 be related in order to have no current flow through the resistor R2? Okay? So this is one condition that we're given to simplify this. The second condition that we're given to simplify this is to say that I2 is equal to 0. Okay? And we can see that that's the case. Again, looking at the problem, it says that if V1 is equal to 2V2, how must R1 and R3 be related in order to have no current flow through the resistor R2? And so no current flowing through the resistor R2 says that I2 is equal to 0. Okay? So what that does for us is we can simplify this equation to start with, and that says that I1 is equal to I3. And I'm just going to call that I from now on. So I is equal to I1 is equal to I3. And anywhere that we see an I2, that's 0. That's 0. Okay? And then this is 0. Okay? So now what we have is a system of two equations, two unknowns. We don't know what R1 is, we don't know what R2 is, but we can relate those to what the V's that we have are. So from this equation, what this says, I'm going to bring this over here. I1 times R1 is equal to V1. And then this one I can bring over here. This says that I3 times R3 is equal to V2. Okay? Now we also saw from this equation that I1 is equal to I3, and that's just equal to I. And from this condition that we were given, that V1 is equal to 2V2, we can simplify this further. And so this equation is now going to say this is I times R1 is equal to V1. And this equation is going to say that I times R3 is equal to, this is the way that I have this here, this is going to be V1 divided by 2. Okay? Now to find some relationship between my R1 and my R3, what we can do is we can just divide this equation by this equation. What that does is it's going to cancel my i's. It's also going to cancel my v1s. And so this says the ratio of R1 to R3 is going to be equal to 1 over a half, which is 2. Okay? And then that's it. So it's a pretty, I wouldn't say standard thing, but it's a fairly common thing to have a problem where you're meant to apply the loop and the junction rules in order to get a system of equations. And then because we don't really want you to solve a complicated system of equations, what we'll do is we'll give you some conditions so that the system of equations that you end up having to solve is much simpler than the system of equations that you started with. Okay? So I'll pause here and see if there's any questions about this. Oop, I froze. Let's fix this. Oh, no. This could be major problems. All right, so come on, this is not. Why does technology do technology things? Oop, I also turn the TV off. Okay, so let's fix this. Oh, of course, now it just doesn't want to respond. Of course, whenever you have to do something important, technology refuses to cooperate. Okay. So I don't really know why I can't get the camera to work again. Sometimes it crashes. So I'm going to try to restart it. Okay. So the camera's fine. It's just the link between the camera and the computer is not working. So, old NASA standard, let's unplug it and plug it back in. And I apologize for this, because this is important. All right, I'm gonna have to stop the stream and start it again, I think, because I have to restart OBS.